Hi there. This is Espin Dolores. I would be delighted to help you with your upcoming presentation. If there's anything you need assistance with, please don't hesitate to reach out to us. Providing exceptional service to you is our highest priority. E-waste impacts on environment, the escalating global concern. Here are the key takeaways from this topic. Global e-waste is increasing. E-waste surpassed 50 million tons globally in 2020 and is projected to reach 74 million tons by 2030, with an annual growth rate of 3%. This increase is due to factors such as the growing ownership of devices like smartphones, wearables, and smart technologies, the increasing reliance on electronic devices for communication, work, and entertainment, and rapid innovation, which leads to shorter product lifespans and frequent upgrades. E-waste consists of discarded electronic devices and equipment that have reached the end of their useful life, encompassing various materials and environmental impacts. The types of e-waste are large household appliances such as refrigerators, air conditioners, and ovens that contains refrigerants, CFCs that harm the ozone layer and other hazardous materials. Small household appliances like toasters, coffee makers, and vacuum cleaners that often improperly discarded in landfills, contributing significantly to waste volume. IT and telecommunications equipment. These are the fastest growing e-waste source, containing valuable metals and hazardous substances. Improper disposal contaminates soil and water. Consumer electronics, including TVs, gaming consoles, and monitors, contains hazardous substances like mercury and rare metals like indium, posing risks to groundwater. Lighting equipment like fluorescent lamps, LEDs, and CFLs contains toxic materials. For example, mercury and rare earth elements can contaminate soil and water. Electric and electronic tools include power tools, lawnmowers, and drills. Improper disposal leads to soil contamination due to hazardous substances like cadmium. Medical devices such as X-ray machines and medical monitors, which contain biologically hazardous materials and chemicals like mercury and lead, requiring careful disposal. Automatic dispensers includes vending machines and ATMs that are made of substantial metal and electronic content, though less frequently discarded. Improper handling of e-waste causes significant environmental damage. Soil and water contamination. Improper disposal of e-waste leads to hazardous chemicals like lead, cadmium, mercury, and brominated flame retardants leaching into soil and groundwater. Leaching process of toxins involves rainwater or groundwater dissolves toxic elements from e-waste, carrying them into soil layers and contaminating groundwater sources. This highly toxic metals that can remain in the soil for long periods can affect the ecosystem through harming the beneficial bacteria, fungi, and earthworms, essential for healthy soils. It also impacts human health. Contaminated soil and water can enter the food chain where prolonged exposure to these substances can lead to neurological issues, kidney damage, and developmental delays, especially in children. Air pollution. Open burning of e-waste, common in informal recycling operations, releases harmful pollutants such as carcinogenic compounds, particulate matter, heavy metals, and polycyclic aromatic hydrocarbons into the atmosphere. These emissions pose significant health risks, including respiratory diseases, asthma, and cardiovascular problems, especially to communities near burning sites. Additionally, long-term exposure increases rates of cancers and developmental disorders. The pollutants can as well cause wider environmental impact as the pollutants released into the atmosphere can travel long distances, impacting air quality on a regional or even global scale. Greenhouse gas emissions. The e-waste sector can contribute to greenhouse gases through several ways. Emission from mining and extraction. Mining metals like copper, gold, and rare earth elements is energy intensive and emits large amounts of carbon dioxide and other greenhouse gases. Device that reaches the end of its life cycle perpetuates emissions by requiring continuous mining of new materials. Recycling emission. Recycling, while essential, often involves energy-intensive processes like smelting, which release carbon dioxide. Additionally, inefficient recycling facilities can exacerbate pollution. Landfill emission. Organic compounds in e-waste decompose anaerobically in landfills, releasing methane, a greenhouse gas significantly more potent than carbon dioxide. Methane emissions from e-waste contribute to climate change over time. Social and economic implications of e-waste include: 1. Health risks. Toxic exposure. Informal e-waste workers face chemical exposure through skin contact and inhalation during unsafe handling or burning of components. Cumulative health effects. Prolonged exposure to hazardous substances can result in chronic health conditions such as cancer, kidney disease, and reproductive disorders. 2. Informal recycling economies. Economic reliance. Communities in regions like Ghana, Nigeria, India, and Pakistan depend heavily on informal e-waste recycling for income. This sector provides low wages and lacks pathways for sustainable economic development. E-waste dumping. High-income countries export e-waste to regions with lax environmental regulations, particularly in Africa and Asia. Unsafe processing in these areas results in environmental injustice, where developing nations bear the burden of waste from wealthier countries. Environmental and health costs. Short-term economic gains are outweighed by long-term consequences, including environmental degradation and adverse health effects. Burning and improper disposal contaminate air, soil, and water, affecting local communities and ecosystems. Mitigating e-waste impacts on environment. Here are several key measures that can be practiced. 1. Stricter regulations and compliance. Governmental policies. Governments should enforce stricter regulations requiring manufacturers to manage the life cycle of their products, ensuring proper disposal and reducing environmental harm. Extended producer responsibility. EPR frameworks hold manufacturers accountable for recycling and safe disposal, incentivizing sustainability in design and production. International regulations. Global policies like the Basel Convention help regulate e-waste exports, preventing hazardous waste from being transferred to developing nations with weaker environmental controls. 2. Promoting circular economy practices. Product reuse and remanufacturing. The circular economy model promotes reusing and remanufacturing products, reducing raw material demand and minimizing environmental footprints. Economic and sustainability benefits. Circular practices conserve resources, reduce waste disposal costs, and create green jobs in sectors like recycling and repair, contributing to sustainability goals. Consumer awareness. Public education campaigns can encourage consumers to make sustainable purchasing decisions and responsibly dispose of e-waste, reducing overall waste generation. 3. Innovative recycling technologies. Hydrometallurgical recycling. This cleaner alternative to smelting uses chemical solutions to recover metals from e-waste, reducing energy use and environmental impact while enabling selective recovery of valuable metals. Automation and AI-driven sorting. AI and robotics improve sorting efficiency in recycling facilities, reducing contamination and enhancing material recovery rates, making recycling operations more economically viable and effective. Thank you so much for taking the time to watch our presentation. We sincerely hope that you found it valuable and informative in some way. If you have any questions, please don't hesitate to reach out to us at info@espincorp.com or visit our website. Once again, thank you for your time and have a wonderful day.